Before I go on to set associative caches, I'd like to talk about the diagram that we just saw. Now, note that this diagram assumes that the TLB is separate from the cache. It's also possible to have the TLB and the cache be the same structure, but that's not very common, especially in today's machine, because you'd like for the address to be translated in parallel with cache lookup. It speeds things up considerably. So which steps over here would be different if the cache were directly mapped? Well, a lot of it's the same. We still take the virtual address and divide it into page number, byte within page, and we still translate the virtual address into a physical address in the same way. We still fetch the block from the cache, the desired bytes from the block, and send the bytes to the processor in the same way. But there is one thing that's different, and that's the part over here where we select the cache victim to be replaced. In a direct map cache, it's just trivial to select the victim because it's got to be the same line that the new block needs to go into. That's the only possible victim, so all you do is throw that line out and bring the new line in. So that's the difference between a direct mapped and a fully associative cache in terms of the flowchart. Not very much difference at all. There's a world of difference in operation just because the comparison for fully associative is so difficult. Instead of comparing a single 7-bit quantity, you're comparing 128 14-bit quantities, but other than that, there really isn't a lot of difference. Set-associative then is a compromise between the two, because often there are just too many conflicts in a direct map cache. Remember that program that I talked about that's just hitting an array whose stride happens to be about the same size as the cache, or a multiple of the cache size. It's going to have lots and lots of conflicts. So we'd like to eliminate some of those conflicts, but we can't afford to go to the very complicated logic required by a fully associative cache. So the way to do something in between is to say, instead of the cache line having only one place to go, or having total freedom about which line to go into, we'll restrict a particular block to going into one of a set of lines. And this means that the cache itself is divided into sets, where the number of sets is a power of 2, and a block that's placed in the cache can go into any line in the set I mod S. So if we have 50 sets, or let's got to be a power of 2, so let's say we have 64 sets, and we have block 65. Well, I mod S, 65 mod 64 is 1, so this block is going to have to go into one of the lines in set 1. And of course, every line has its own tag associated with it. Now, because in this particular example we're going to deal with 2 lines per set, then any block that we want to put into the cache can go in one of 2 places. It can go in line 0 or line 1 in the set that it has to go in. So we have a choice of 2 places where we can put any particular block that needs to go into the cache. And that means that the main memory address is composed pretty much as we saw before when we talked about direct map caches. It contains an offset which is 4 bits long, because we could put it in any one of the 16 bytes or words within the line. I say we can put it in. I mean the referenced byte or word could be any one of 16 different bytes or words in the cache line. So that's why the offset field is 4, which is the log of 16. And then the index field just determines which set the block goes into. And since there are 64 sets here, that's because there's 2 lines per set, and there's 128 lines. That means we've got 64 sets. That means that we've got a 6-bit field that tells which set it goes into. And then whatever is left over is the tag, which in this case is 8 bits. And so you can see that we have 2 sets per line. That's called two-way set associative. If we had 4-way set associative, we'd have larger sets but fewer of them. If we had 8-way set associative, we'd have even larger sets but fewer of them. And the logical end to all of that is just to have one set but have all the lines in it. And that's the same as a fully associative cache. So that's the way that we have a compromise between the direct mapped and the fully associative cache. Okay, so I got some exercises for you. Those are going to be quiz 2C for this week. But in the meantime, what I'd like to do is talk a little bit about how we choose a word out of a set associative cache. The first thing we need to do is determine the proper set, and all we do for that is just to take I, which is the line number, mod the number of sets, and that tells us which set that line is going to go into, or which set that block is going to go into, block I. And then we look at the leading 8 bits of the address, which is the tag field. We compare them with the tag of all the lines in the set. So remember I told you that for a direct mapped cache we have only one 7-bit comparison. For a 2-way set associative cache we have two 8-bit comparisons. And for a 4-way set associative cache we'd have 4 9-bit comparisons and so forth. So that's the way that the associativity factors into the number of comparisons and the length of the comparisons that you need to do. So once you've done that comparison, if you have the leading 8 bits of the address match any of the tags, then the block is in the cache. So at the same time we're doing this comparison, we can read out the first bytes or words of the lines so that they'll be accessible at the end of the cycle. So you determine where in the set the hit is. In the meantime, you're reading out the first bytes or word of all the lines in the set. And then if there's a match, you just take the data from the block from the block that was actually in the cache, the block that hit in the that's where you hit in the cache, and then put that out onto the right line. So you see here what happens is that you're doing all the comparisons in parallel for the different lines in the set, and then if there is a hit, then you select that particular line from the set. There's S lines in the set. I'm sorry. There's there's the number of lines mod S, or number of lines divided by S. Lines within a set. So like if it's a 4-way set associative cache, there's 4 lines coming out here, and you just select the one that hit and gate that output into the cache buffer, and then from there to the processor that needs it. Okay, well, in terms of design, all reads from the cache occur as early as possible to allow maximum time to do the comparison, but you try to defer the judgment of which line hit, which line you need to use, because by that time you'd like the data to be in high-speed registers so the processor can receive the data fast. So that's the way you deal with the set associative cache. Now, just got one more point to make in this section, and that is that line length is dependent upon various factors. If you have long lines, you probably have, up to a point anyway, higher hit ratios, because let's think of you walking through an array. If you're going to walk through 1,000 words of the array, the longer the line is, the fewer the lines that are actually going to miss in there, fewer the references that are actually going to miss in the cache, because you bring in more data each time you have a miss. Long lines are also advantageous in that they mean that less memory is devoted to tags. The cache has to hold the tags as well as the data bits, and if there's too many tags, then that just cuts down on the number of data bits that can be held in the cache. Long lines also mean longer memory transactions, which in a uniprocessor, who cares, because the bus is there for the references between the processor and memory. But in a multiprocessor, you may have many processors trying to share the bus, and long transactions gum up the works by making any other transaction that wants to use the bus wait until they're done. So it's undesirable to have long memory transactions in a multiprocessor. Further, long lines cause more write-backs, and that's just because the data may have changed. The longer the line, the greater the chance that the data have changed. And then when you have to throw that line out of the cache, you can't just discard it, but you've got to write it back. So I'll talk about that in a little bit more detail later. I say for most processors, line sizes between 64 and 128 bytes perform best, and that's a little bit outdated. I'd say 128 to 256 today, but there's some still that are 64 bytes. And then I already gave you the definition of B-way set associative. That means there are B lines in each set. So how many way set associative is this example above, right there? Think about that for a minute. Oops. Yeah, think about that for a minute. How many way set associative is that? Okay, well, there are a lot of caches in the real world that are 2, 4, or 8-way set associative. And there are even some that are 16-way set associative. But as B increases beyond that, the cycle time starts to climb just because you've got more comparisons to do, more levels of logic to transit in addition to there being more logic because you're doing more comparisons in parallel. And things just get slower. Okay. So the higher cycle time begins to offset the increased associativity. Almost all L1 caches are no more than 4-way set associative, but L2 caches, haven't talked about levels yet, have I? I think I might have mentioned it on the first day of class, but if you have multiple levels of cache, we'll talk about that in a moment, but if you have multiple levels of cache, then you go first to the L1 cache, level 1 cache. If you don't find the word there, then you reference next the second cache, which is the L2 cache. So I said that L2 caches often have higher associativity. And if you think about that, it's not hard to decide why that might be. Because in an L1 cache, the references need to be handled very quickly. So you can't afford to go through lots of levels of logic. On the other hand, an L2 cache is not referenced that frequently, so it can legitimately take longer to complete the reference. So you can afford to have more associativity. Okay, good.